on component separation by Mark Ashdown.
Good morning. So I'm going to talk to you about the CMB targeted component separation. So, first of all, I'll start with the acknowledgements. All of the institutions and funding bodies involved in Planck. So you'll see this in every Planck collaboration talk. So first of all, talk about the inputs to component separation. So we take the data, the maps that are made by the two instruments. The frequency map level. We also take the half ring maps, which are made from the first half and second half of each pointing period. They can tell us something about the instrumental noise in each frequency channel. We take the beam transfer functions, all of the sort of knowledge of the instrument, beam transfer functions, band passes, and so on, and the most important ones. And also the source catalogs and the masks, which are made from them as well. And in addition to taking the inputs for the real data, we also take a set of simulations as well, the so-called full focal plane simulations. These are the sixth iteration of it, so they're called FFP6 here. And these are simulated on the basis of the real pointing from the instruments, the real flags, the measured beams and band passes. I have an input sky which is generated by the Planck sky model. And we generate the maps in the same way as the real data is generated by simulating timelines and then making maps from them with a map making code. So the output from the simulation is a set of observed frequency maps plus the half ring maps and all the subsets of the data that we can generate for the real data. Maps are the individual input components, which are good for us for validating our component separation. And in addition to that, a set of Monte Carlo realizations of the cosmic microwave background and the instrumental noise. How we do the component separation? Well, we actually decided to exploit the redundancy here to try to sort of validate our methods as much as possible internally. We use four different algorithms. There are two which are based on model fitting. One which is based on a Bayesian parameter fitting. It's called commander ruler. It's a pixel-based method, and it fits a parameterized model of the CMB plus foreground, so a physical parameterization. In fact, it's a two-stage process. The first is called commander, which does MCMC sampling of the amplitudes and spectral parameters. So you get a low resolution, it's a solution for all of the foregrounds plus the CMB. And then there's a second stage called ruler, which gets high-resolution maps of the amplitudes of the foregrounds using the spectral parameters from the low resolution. So this one uses just 7 channels, so you can ignore the top 2 HFI channels, and the map that's produced with it comes out at around 7.4 arcminutes resolution. Another solution for the CMB, which uses model fitting, which is called SMECA, works in the harmonic domain, and fits a model of CMB plus a general sort of foreground model to the cross and auto spectra of the maps, and then solves the amplitude of the CMB maps. This one uses all of the frequency channels, comes out with a 5 arcminute resolution and maximum multipole of 4000. And you will see, well, you have seen already a version of this CMB map which is filled with a constrained realization in the processing mask. So 3% of the sky was filled with that. There are other two methods which we use, which are based on sort of blind methods. They minimize the variance of the CMB component. There's an internal linear combination. Needlet ILZ works in the wavelet or needlet domain, and it makes a combination of the data at each needlet scale independently. In this one, uses 8 channels. The LFI 30 gigahertz channel was dropped from this one. It does it at 5 arcminute resolution and maximum multipole of 3200. And the final method was template fitting, which works in the pixel domain and makes templates by subtracting frequency channels from each other to get rid of the CMB, so just foreground components in it. And then the templates are used to clean two frequency channel maps, the 143 and 217. And these maps are combined afterwards. These two are combined afterwards in a harmonic space to produce a single CMB map for our purposes here. And it's a 5 arc-minute resolution again, and the maximum multipole of 3100. So these are the 4 CMB maps that are produced by these 4 methods. And of course, you can see that at large scales, they agree with each other, which is very reassuring. And you can see the residual galactic contamination in the galactic plane here. You don't see it in the SMECA map because a processing mask has been applied here to stop, because it works in a harmonic space, so to stop the residuals leaking from low galactic latitudes to high galactic latitudes. Hence this smooth appearance here in the galactic plane. So each of the methods also provided us a mask as well. This is what we call a confidence mask, which is based, on each individual method's assessment of the statistical robustness of the solution. They've been defined with the various degrees of conservatism in them. So this is the Commander Ruler and Seven more conservative than the masks provided by Nilk and SMECA. And in the analysis, you'll see in this, in the rest of this talk, we actually use the union of these masks here, so this leaves 73% of the sky for the analysis. So to characterize the maps, I want to look at their beam transfer functions. 3 of them are at 5 arc-minute resolution, so they're ones here. They differ in the treatment of the pixel window function of the map, so they look slightly different at high L. It's a fall off here from needless IRC because it works in with a set of wavelets, which the last window for goes to 0 at L of 3200. And Commander Ruler is slightly lower resolution. It works in pixel space. That's a resolution of around 7.4 arc-minutes. So if you look at the differences between these maps, I should point out, of course, that the color scale here is minus to plus 30 microkelvins. The color scale you saw before was 10 times that. And you can see the pairwise differences, difference between each pair of methods. And you can see, of course, differences in the galactic plane, as you'd expect. But there are also some differences at high galactic latitude, which may be due to residual zodiacal light emission. Possibly it's to do with the combination of frequency channels that are used for it. But outside the galactic plane, we see residuals typically less than 5 microkelvins in each of these pixels. And some of the maps have discontinuities because their masks, sort of different weights are applied in different regions of the sky. That's reassuring. So we can actually look at the performance of our component separation methods by looking at the residuals from our simulation. So these are the FFP6 simulations. So this is the CMB map from the output of the method. We've subtracted off the CMB map, which is propagated through each of the pipelines. So this is all of the residual contributions to the maps, the residual foregrounds, and the noise. And you can see that general, we're doing reasonably well outside the galactic plane. The SMECA here, this code here, has the smallest residuals at large angular scales. One note of caution in this, in that if we do the same pairwise difference between the solutions, do the same check, we actually see that the residuals in our simulations are larger than in the real data in the galactic plane. Certainly, we don't see the large-scale structures outside the galactic plane, but we do actually see a sort of larger differences in the pair. If I go back 2 slides, you can see that the residuals in the galactic plane are actually smaller in the real data, which means that we should exercise some caution when using the results of the simulations. Maybe the foregrounds are actually more complicated than in the real sky. So first thing to do with these maps is to look at, sort of beyond that, actually looking at the map level, is to look at the power spectrum and cosmological parameters. And here we want to ensure that these maps are consistent with the high L power spectrum, which was used basically based on cross-spectrum methods of frequency channels or detector sets. So these CMB maps are used for higher order statistics. And it's also in the analysis here, we use a larger sky fraction, as in the sort of the conservative one that was adopted for the likelihood analysis. We've used XFaster, power spectrum code, to estimate the spectrum, and a correlated Gaussian likelihood to evaluate the cosmological parameters. So the half-ring, half-difference map, so these half-ring maps can be used to assess the noise. Multiple range that was used for this is 70 to 2000, and a strong prior was put on tau because we don't using the lower likelihood or any polarization. And so residual foregrounds are modeled in the power spectrum with just two templates. There's a Poisson component with a constant power spectrum, and the clustered component, which is DL, that's L squared CL over 2 pi, goes as L to the 0.8. There are some limitations, of course, to this analysis. We've not accounted for some of the systematics that are in the likelihood. We don't take into account the uncertainties in our beam transfer functions, nor do we take into account uncertainties in the intercalibration between the channels. And we have a simple foreground model. Anyways, just look at the power spectra of the foreground clean CMB maps. There are two lines here for each of the maps. There's the power spectrum of the map itself. You can see the CMB, plus the tail from the noise as it goes up there. These have been evaluated using the R73% mask, and the spectra have been corrected for the effects of the mask and the beams. The lower line here is our estimate of the noise in each of these maps taken from this half-ring, half-difference map. And you can see here that the Commander ruler is noisier than the other three methods, which have comparable noise at small angular scales. And you can see here some ripples in the noise, which is due to the adaptation of the methods at large angular scales to try to reduce the foregrounds as much as possible. In order to, sort of get a handle on the contributions to the power spectra, we can look at our FFP6 simulations. So this shows you 3 lines for each of the methods. There's the propagation of the CMB component through the pipelines, the propagation of the noise, which is shown in the dot dash line here, and the propagation of the foregrounds, which are shown in so we see the residual foreground contributions here, and we see that they're becoming comparable to the CMB signal level at around L of 2000. At large angular scales, we see that SMICA performs best. It has the lowest power spectrum here of residual foregrounds, which is borne out by our difference maps between the inputs and the outputs. So if you take these noise estimates, match in signal and plus noise estimates at noise estimates, and actually make the CMB power spectrum estimate, this is what we get. The solid line for each code shows the estimate after subtracting the best fit residual foreground model. That's fitted between L of 70 and 2000. And the dashed line shows the spectrum before subtracting the residual foreground model. We have some noise left over, even after we use the half-ring, half-difference map to estimate the noise level, because there is a slight bias in that noise estimation due to the correlations induced by the HFI glitch removal between the two halves of each pointing period. And the error bars here are computed using the Fisher matrix of the solution. We use this. These are the cosmological parameters which come out. This is done for comparison purposes between the 4 codes, the 4 methods that have been used to produce the CMB maps, plus 2 CamSpec, which is the official high R likelihood, and PLIC as well, which is one of the alternatives. Foreground parameters, these 2 here, are not shown for CamSpec and PLIC because they use a different foreground model. So this is the amplitude of point sources, this is the amplitude of clustering components. So the excess noise I talked about is actually being absorbed into the foreground parameters. You see that the Commander ruler is noisier, and therefore the foreground parameters have a higher value there. But on the whole, for the cosmological parameters, we're getting values which are consistent with the main likelihood analysis. And taking into account the limitations of the likelihood used here, it's a good result. And we can be confident that our CMB maps, the power spectrum, and the higher order statistics we get from them are consistent with the main cosmological analysis via the power spectrum. In order to sort of evaluate the methods, we've also made sort of tests of the higher order statistics. In our simulations, we put in a known non-Gaussianity, put an FNL local, which is 20.4075. The value I think was chosen at random, so we didn't actually know precise value. And you see how each of the methods recovered this FNL. We can see that the Needlet ILC and SMECA perform best in these tests. They get values which are almost identical to the inputs and sort of good uncertainties there. Also, we looked at the gravitational lensing by large-scale structure, see how they recovered when we have a known input, a known input power spectrum. So this shows you the power spectrum of lensing potential recovered by all four methods. The black line is the input, and the lines with error bars are the recovered values, and the lower panel shows the residuals. And we can see that over 70% of the sky, we're recovering the lensing potential power spectrum very well. The uncertainties results are all in agreement between the four methods, and the uncertainties on the commander ruler are slightly larger due to the larger beam, slightly lower signal to noise to lensing. So conclusions from this. So we know that all four of the algorithms work well on the real and simulated data. We've shown they get consistent results. For the low L power spectrum, you usually choose the commander maps. These are the ones that have been produced using the MCMC sampling. So you have the ability to marginalize over the foreground residuals there. That's essential since the foregrounds dominate at large angular scales. For the high L analysis, we've chosen SMECA as the leading method because it performs best on the simulations, both in terms of the foreground residuals and the preservation of the primordial non-Gaussianity signal when we inject it with a known signal in there. And we use the other maps to assess the consistency of the analysis. There are still uncertainties in this due to the choice of methods and the assumptions that they make. So we use more than one map to try to get a handle on the uncertainties due to that. Some of the things that I've mentioned today in passing, but we've mentioned in other talks, the Planck sky model, full focal plane simulations, and a couple of sort of descriptions of the methods themselves will be in the parallel sessions on Thursday. And I shall end by showing you this, which is the SMECA foreground cleaned CMB map. And this is the 3% processing mask has been filled with a constrained realization, which was what was mentioned before. So you don't see the residuals in the galactic plane. So.
Thank you, Mark. Do you hear me?
No.
Okay, so again, we have some time for questions. Understand everybody wants to have a coffee, but not yet. We still have a presentation to go. No question? Okay.